Good day, and thank you for assisting to this virtual talk in the frame of the International Conference on Coastal Engineering. My name is Toni Llull, and I'm a PhD student in the Polytechnic University of Catalonia. I'm working on the Laboratory of Maritime Engineering, and I will present a set of experiments on twin-propeller-induced scour near quay walls that we performed in our lab. First of all, a little bit of an introduction. We all know that the scour due to ship propellers has been traditionally a problem for port authorities and engineers to design and maintain harbor structures. And due to the increase in maritime traffic in the last decades, the ships became bigger and more powerful. So the scouring due to propeller action problem is still ongoing. Existing formulae is experimental based and mainly focused in a unconfined and single propeller scour, which is not the cases that we are facing in that field. Controllable pitch twin propellers, for example, are the main systems used by ferry ships or ro-ro ships, but they are barely studied so far. And this is why a set of experiments in confined scour due to twin propeller with two different pitch radials is presented here. This is our experimental setup, a 12 meters length concrete basin with a twin propeller model, as we can see here in the plain view. The axes are separated by two diameters, 2 dps, and we are performing experiments at 7 and 10 dps and 1 dp and 1.5 dps above the sandbed. This is the measuring area, and we can see here that the measuring area for the experiments on pitch 0.9 propellers was a little bit shorter than the one for pitch 1.0 experiments, but we'll talk about it later. It's just to have it in mind because we had a larger blanking area in the pitch 0.9 experiment. At the end, we are presenting 24 experiments of 30 minutes with bed spanning every 5 minutes, and we have two different pitch ratios, two different distances to the front wall, two different bed clearance, and 3 speeds of rotations, and this difference in the blanking distance between one and the other set of the experiments that we will mention later in the methodology. First part of the methodology is that we must mention that we are using in this presentation only the center line profiles because we are just analyzing erosion depths, so maximum scour depth. And since the scour holes are symmetrical on its axis, the center line depth is the profile that better fits with the maximum depth profile. So we will show in the results the agreement between the maximum depth and its corresponding central line depth, and you will see that it's pretty good. Then second part of the methodology is the Scour profile categorization. So we basically categorize the 3 kinds of profiles that we find at the end of the experiments, and you can find it also in literature. When you are performing experiments on confined scour, you end up with either this kind of no-merged profile, what we call no-merged profile, which is a profile that is clearly distinguishable how there are 2 different scour holes. The one which we named harbor basin hole is the one that is caused by the direct impact of the propeller jet into the sandbed. The second one, which we named front wall hole, is the one that is caused by the impact of the returning flow after the jet impinges into the front wall. Second type of profiles that we categorize is the transition to merge profiles, in which we still can find this 2-hole profile, 2 different hole shape, but the first harbor basin hole or primary hole is already merging with the second one, and the totally merged profile, in which we just find one big front wall hole. This is an explanation of the methodology that we follow to assign a category to each one of the profiles, but since I don't want to spend a lot of time here, I will kindly ask you that if you are interested in this methodology, you can ask me in the questions. Anyway, as you can see, the slope profile is used to categorize every profile. And then in the front wall profile in pitch 09 experiments, as I said, the measuring area was enlarged between the two sets of experimental works. And in the pitch 1.0 experiments, we had a flanking distance of 0.05 meters to the front wall, while in the pitch 09 experiments, we had a larger flanking area, flanking distance, 0.25 meters to the front wall. Thus, new fitted profiles were needed for pitch 09 experiments, and that's why, first of all, we dimensionalize every profile in pitch 1.0 in order to see which with polynomial we can fit the unknown part of the profile of pitch 09. We end up with a good fitting of a 3-degree polynomial in the no-merged and transition profiles, while the merged profiles were fitted with a 5th degree, and all of this is in the case of pitch 1.0, which is assumed to be the same in the case of pitch 0.9. And those are results. First of all, results of the comparison between the center line depths and the maximum depth along the whole y-axis. This is done at every x in the whole measuring area with a delta x of 0.01 meters. And we basically get an almost perfect agreement between the depth measured at the center line and its corresponding depth measured in the maximum depth position. And then about the new profiles fitting, these are some results of the profile fittings. You can see here in the left part of every plot that the profile is elongated until it reaches the front wall. And in this case, in pitch 1.0 cases, like the one that I'm showing, it is also applied. The same methodology is applied in order to have validation of the method. And basically, we find a very, very good agreement between the results that we predicted with the elongated polynomials and the real measures. And at the end, this was used to compare depths, maximum depth of a scour near the front wall between every case. And first, we can check equation 1 and equation 2. They are used to obtain the thrust, equation 1. And to obtain it, we need the coefficient of thrust of every propeller, which is obtained with equation 2, which is just actual momentum theory. And the U sub 0 is obtained experimentally. Also, if you want to know the method that we follow to obtain the U sub 0, I can explain it in the comments, but I'm not spending a lot of time in here neither. And basically, we obtained a different cat E depending on the pitch ratio as expected. In this case, it's 0.55 and 0.65 for 0.9 pitch and 1.0 pitch, leading us to obtain a different thrust for every propeller. And in this plot, the erosion is non-dimensionalized with the diameter of the propeller, and is plotted against this thrust. In order to see that when we change the thrust because of the change in the speed of rotation, this is the black, dark gray, and gray colors. This is 300, 350, and 400 RPMs. When we change the thrust because of the change in the RPMs, we see a clear and linear increase in most of the cases of the scour depth. But it's not the effect that we have when we change the thrust due to the change in the pitch, which are the dashed and no dashed boxes. You can see here. And for example, this is the 350 RPMs. And in this case, we are in the blue star and circle. So we are in the emerging case, that is the 70p Cmax. And we don't see, in this case or in any other individual case, significant difference between the change in the scouring depth due to the change in pitch. Same analysis is done for the x equals 0.25 meters from the wall, because it's the closest position in which we don't have a fitted profile. So this is direct comparison of measures, but same trend is observed. And at the end, we are also comparing at the maximum depth at the harbor basin. And in here, what is interesting is that we don't see changes even if we are changing the speed of rotation in the harbor basin hull, because at some point the harbor basin hull reaches a threshold in which every profile becomes a merged profile. So these measures in here, these blue measures are the same than in here, because when it's merged, there is no distinction between the two hulls. And when it's not merged, any of the harbor basin maximum depth can overcome this merging threshold without becoming a merged profile. So either it reaches a static state, in which these cases at 300 RPM at any pitch reaches an static state, or it becomes a merged profile. And then some equations from the literature are applied in order to compare with our experimental results. And what we see is that applying the Payang method, which is the only one in literature that is considering twin propeller confined scour, we basically have an under prediction of our experimental results. So as conclusions, the study of the maximum depth evolution is performed with the center profile in the twin propeller model. The front wall profiling is determined with the slopes of the profile itself. No difference are observed between pitch ratio, although the thrust do change. And the experiment in confined twin propeller score, since they are lacking literature, the only equations considering this scenario clearly underestimate the final scour depth. And this is the end of the presentation, and I wish you to have a very good virtual conference. And for any questions and comments regarding to this presentation, I will be glad to receive them via the conference platform. So thank you very much for assisting, and have a good day.